The objective of this video is to review and summarize fields in an electric machine. We're going to start by talking about the magnetizing field, and this is also called the magnetic loading of the machine. So the magnetizing field, or the no-load field, or the magnetic loading, is the field that is always present in your machine, regardless of if you have any current flowing in your stator. In a permanent magnet motor, this is established by the magnets on the rotor. As an example, I've drawn here a 4-pole permanent magnet rotor with surface-mounted permanent magnets. This magnetizing field could also be established by your rotor bars in the case of a squirrel cage induction motor, or your field winding in a salient pole wound rotor. What we say is that this field has got p pole pairs, lowercase p pole pairs. And in this case, I've drawn a 4-pole rotor, which means that little p is 2, because we have 2 pole pairs. And I'm labeling on here some of the conventions that we use. The first is I've labeled the angle theta mech, that stands for theta mechanical, and that is the number of radians to our direct axis from our x-axis. So if x points that way and y points up here, theta mech is the number of mechanical radians, the number of radians from our x-axis to where our north pole is aligned. And then we can also draw some arbitrary vector in the to the air gap of our machine and note the cylindrical coordinates. So we have a cylindrical unit vector of phi hat and a cylindrical radial vector of r hat, a unit vector of phi hat and r hat. And this arbitrary location can be described by an angle of alpha. And always in my notes, we assume that the rotor is rotating in the counterclockwise direction at some speed omega. Okay, so we can take this and we can make a plot of what our field looks like in the air gap of our machine. And if we assume that we have sinusoidal magnetization, we like to assume this, that we have no harmonics, then our plot looks something like this. And in our case, this is phase shifted because our rotor is rotated a ways, and it's phase shifted by theta mechanical degrees. So this can be described by the equation that b delta of alpha is equal to some peak, b delta hat, times the cosine. And we like to write it in this form here, where we multiply p through, so we have p alpha minus p theta mechanical, and then we call the quantity p theta mechanical as just theta. And that stands for the rotor angle in electric radians. And so if you see me writing theta, it means that it's the rotor angle in electric radians. It can be translated to p times theta mechanical. The other quantity of interest here is this peak value, b delta hat, and this is called the magnetic loading of the machine. It's a fundamental property of the machine. It's based on the steel that you use in your machine, and it can only assume certain values based on the material type that you've chosen. So steel saturates at a certain point. A low-grade silicon steel maybe saturates at around 1.5 Tesla, and because you have teeth in your typical machine design that have to concentrate the flux and carry that flux, your tooth will saturate around 1.5 Tesla, which means that your air gap is at a lower field level. And typical values that you see in machine designs range between 0.7 Tesla to 1.05 Tesla. High-speed machines will typically use lower field values due to losses, and also because they've got smaller laminations, smaller thickness of laminations, and so they're unable to carry greater field levels. So at the small end here, this is higher speed, and it might even go down to like 0.5 Tesla. And at the upper end here, you've got low speed, very torque-dense machines. So this is useful to know because when you're solving for forces and torques in your machine equations, it helps to understand what the physical fundamental parameters are of your machine to know whether terms are significant or how to dimension and size your motor. And in other videos, you can see this type of material presented as the machine sizing laws. We're actually going to derive that in a later video as well. But just to make you aware of this, I want to highlight the key features and the key properties of machines. And for the magnetizing field, this is the fundamental property. It's called the magnetic loading. And Of course, in practical machines, your air gap field has harmonics, so maybe it looks something like this. And you can use a Fourier series to represent all these harmonics. So you might write this as follows. But we are going to focus, for now anyway, on the case of no harmonics, where we only have our fundamental component, so this expression. Okay, that was a quick one. Next, we're going to talk about motor windings, and this is going to take a little more time. So I've drawn a 6-slot stator here, and I've just placed a couple of coils in. This is kind of an arbitrary drawing. My purpose is to remind you that we can take a motor geometry with teeth and slots and coils and cast it as an equivalent surface current density, or that is a current density on the inner bore of our stator. So we can take this drawing that I've got right here, and we can cast it, or we can draw an equivalent diagram of a slotless stator, where on the inner bore of our stator we have an axially directed, infinitesimally thin surface current that produces an equivalent set of fields. And we do this because it gives us a physical basis for setting up winding functions and analyzing the magnetic fields in our air gap based on harmonic content. And so you can see I've sketched phase U, and I've drawn this for a 2-pole winding. You can see that I've got dots on the top of the page to indicate that there's current coming out of the page at us, and that is again the surface current density. That's an infinitesimally thin layer on the inner bore of our stator. And on the bottom of the diagram, I've got X's going into the page to indicate that there is current traveling into the bore of into the stator. And so the size of the conductors is supposed to indicate the amount of current at any given location. You can see I've drawn it as peaking at one location, so you might assume that this is perhaps a purely sinusoidal current density. It doesn't have to be. This is a general form, but the point is that we've taken a discrete set of coils and slots, and we're then drawing it as this equivalent current density that allows us to study it a bit easier. And so what we do is we've got phase U, and then we can do the same thing for phases V and W. And so each of the phases is spatially displaced from the other phases by 2 pi by 3 divided by p. So the 2 pi by 3 is because it's a 3-phase system, and the p is because that's the number of pole pairs. So if you had a 4-pole motor, this would be pi by 3 spacing, because little p would be 2. And remember, this is a review. You can find the content of and the derivation of all of this in other videos. Okay, so we call this quantity a circumferential current density because we can talk about any angle alpha in our machine. So we can pick some arbitrary angle and quantify the entire current that's at that location as being AC of alpha, and that's in units of amps per radian. And it's positive in the plus z direction, so the plus z direction is coming out of the page at us. So ideally, we have purely sinusoidal surface current density, so if we neglect all harmonics. So this design right here has harmonics because of the slots. But if we pretend that they're not there, or if we only talk about the fundamental component, we can write expressions for our surface current densities of each phase as follows. And what you see is that you got the same sinusoidal function multiplied by a current for each of the 3 phases. It's just that the sinusoidal function is phase shifted by these angles that we labeled up here. So we've got alpha u right here, we've got alpha v over here, and alpha w over here. And that angle is 90 degrees offset from where the phase current, surface current density is peaking. So for some reason this won't let me draw on top of my diagram here, but here phase u is peaking at 90 degrees, and alpha u is labeled 90 degrees before that, so it's at 0 degrees. So as drawn right now, alpha u equals 0. We have these expressions for our angles. And you can have an offset on all these angles, so this alpha u is really the angle between the phase u axis and the x-axis. So up here I indicated the x-axis right here. It's important that all the angles are referenced to the same axis, so theta mechanical must be referenced to the x-axis, and so must phases u, v, and w. So must the phase axes of those phases. So the bottom line is that we notice that we have this portion of each of these expressions that repeats itself. So each phase has got, you can say, the same turns located on the inner board of the stator, the same number of conductors located on the inner board of the stator, but shifted from each other by the phase axis angle. And so we can draw that out as this function down here. And when you integrate this function, you derive the windings function or the turns function of the machine. And this is talked about in different classes and different videos. And so we define this function down here so that we can conveniently express our circumferential current densities in terms of it. We can again capture the impact of harmonics as a Fourier series. Okay, great. So we've defined this repeated function, which describes the number of conductors located, or the magnitude of the current that's located on the inner board of our stator relative to the actual terminal current value. Now let's use it to construct a cumulative circumferential current density. Let's say that we've got three-phase currents flowing. What is the total circumferential current density acting on the inner board of our stator? So what I'm doing is I'm taking these expressions and I'm summing them up. So that's what this is down here. And then I'm going to plug in this function for each of these expressions, but I'm going to do this as a cosine. So I'm going to subtract off pi by 2. And the reason I'm doing that is because I'm going to take this to the phasor domain, and usually as electrical engineers we play with cosines in the phasor domain, and we just keep track of our pi by 2 and convert it back to sine after we've done all of our phasor math. So you could keep this all as sines, it would be equivalent, but I'm doing it as cosines because that is what we are most comfortable working with. And then I'm going to invert these arguments. So I'm going to take the negative of these arguments, and that's because the cosine of a negative angle is equal to the same thing as the cosine of a positive angle. And I'm doing that because it's going to be convenient for our math later. So I'm making all of these have the opposite sign. Okay, so if I do this and I now take it to the phasor domain, we have a familiar expression that results in terms of our phase currents. This is, in fact, our current space vector. And this should be a quantity that you're familiar with from your other coursework. By definition, the current space vector is phase u plus a phase u quantity plus a phase v quantity times e to the j 2 pi by 3 plus a phase w quantity times e to the j 4 pi by 3. That is the definition of a space vector. And so we can see that we've arrived at this expression by our manipulation up here. And so we can replace it then with that current space vector. And in typical situations, you have three-phase balanced currents, which you can write in the following form. And if you take these currents and you plug them into this expression to find your current space vector, you can prove to yourself that you'll get the following result. This is an important result from your drives classes. If you're not familiar with it, I encourage you to do the math and prove it to yourself. You'll use it time and again when it comes to analyzing motor systems. And so now if we go back and we plug this result into this expression, we're now ready to solve for AC of alpha. Where this quantity right here is the magnitude of our current space vector, We can see that right here. These match. And this entire angle right here is the angle of our current space vector. So this is an important result. This means that when we flow three-phase balanced currents, which can always be described, three-phase balanced currents can always be described in this form, we're able to produce an equivalent surface current density in the inner bore of our stator that is at the angle of the current space vector, and we can control the magnitude by controlling the magnitude of the current space vector. We've gone from having a three-phase system where each phase produces an individual circumferential current density, so we have three equations up here, to now modeling this as an equivalent circumferential current density with one equation based on the angle of our current space vector and the magnitude. So we can control where the magnetic field is appearing in the air gap of our motor simply by controlling the phase angle of the three-phase currents that we are flowing. And this is going to be an important result for driving torque and force expressions. So that is the equivalent circumferential current density. Now let's talk about linear current density, or electric loading. And the idea of a linear current density is that we can unroll our stator to construct a linear machine of equivalent dimensions. And so I've sketched this unrolled machine here on the right side, and you can see that now we're referencing it in linear dimensions. So, we can have an equivalent x distance or linear distance in terms of the radius of our conductors, in terms of this length here, and in terms of the angle that we're interested in. So if we move around here circumferentially, like this, at a certain radius, we can translate that to a linear distance. And so the idea of the linear current density is that instead of evaluating this surface current in units of amps per radian, we evaluate it in units of amps per meter. And to understand this mapping that I've indicated above, you can look at this, this arc length here, where our linear distance is the distance we're traveling around the arc length, which is a distance of alpha times r. If we have a circumferential current density, which we've derived from our actual machine, which has stator slots and teeth and discrete coils, so that's this machine over here. We've taken this design and we've constructed this equivalent design over here on the right. Now we want to know how to get from that equivalent design to yet another equivalent design, which is the linear current density. And so we can figure that out as follows. We can figure that out by calculating the total current that's enclosed in a path here. And so for the circumferential current density, we're integrating our function as a function of alpha. And the linear current density, we would integrate over a linear distance x. So we have these differentials x and differential alpha, which we can go back to our calculus days and equate as follows. And so we see that we can convert between a linear and a circumferential current density by just either dividing or multiplying by r, as I've shown in this blue box. And so we can use this to construct our expression for our linear current density, just strictly the fundamental component, as going by the sign of alpha. And this is the exact same form that we had for our circumferential current density up here. But now, of course, our peak value is going to be in terms of a radius. And the reason that we've done all this is that this peak value is called the electric loading of our machine, and it is a fundamental building block or fundamental parameter, just like magnetic loading was. So while magnetic loading was based on our material capability to carry field without saturating, our electric loading is based on our ability to cool our machine. And so what you find is that you can typically achieve 30 to 80 kiloamps RMS per meter if you use air cooling, and if you use liquid cooling, you can get more. And so the reason that we go to this great length is because we're trying to identify the fundamental aspects of our machine so that we can draw conclusions, we know how to dimension it, we can figure out what terms in our force and torque expressions are significant and what terms do not matter. And these rules of thumb for values of electric and magnetic loading are based on actual design practices. So these are empirical rules. The magnetic loading is a little bit better defined because we simply know that our steel can only carry a certain maximum amount of field, whereas electric loading, these are values that you'd look up in like a design handbook for what you can reasonably achieve with your cooling capability. If you're a really innovative mechanical engineer and you have some great idea to extract heat flux, more heat flux from a system, maybe you can do better with your electric loading because you can cool it better. But the point is that these are typical values that are used, and they're independent of the number of poles of your machine. They're independent of the radius of your machine. They're independent of everything. So you start with these building blocks, and then you work backwards to figure out what these values in here should take on. We're now ready to put together the main conclusion from the winding section of today's video, which is our field calculations for a motor winding. And so we'll summarize this as follows. And I want to point out that these conclusions apply only to the case where you have a cylindrical rotor that is centered in your air gap. In the normal direction, so that is the radial direction, you have the following fields. And the first thing to remark on is the MMF, or the current linkage, which can be derived from our circumferential current density as this expression. And then in the traditional way, we can calculate our radial magnetic field in the air gap. And we also have fields in the tangential direction. That's in the phi hat direction. And in a different video, I show you how you can calculate this field given a circumferential current density or given a linear current density. And it ends up just being negative mu naught times your linear current density. So the big conclusion is that we can get a field in the normal direction from our circumferential current density, from our current space vector. We can get a field in the normal direction that we can control the location of by controlling the angle of our current space vector. So first we get a field in the normal direction, and then secondly we get a field in the tangential direction, or the phi hat direction, that we also control the location of by our current space vector. In subsequent videos, we're going to use these fields along with the magnetic loading, along with this field right here, to calculate forces and torques on our rotor. So in summary, this video has gone over quickly the magnetizing field and magnetic loading of a motor. Then we've talked about motor windings and how we can go from a physical winding that we actually install in a machine to an equivalent winding that we can study in terms of its Fourier components, and derived how we can use a three-phase winding to create a rotating circumferential current density on the inner bore of our stator. And from this, we can get the magnetic fields that are in the air gap of our machine.